Good morning. I want to thank, first of all, to all the people in the Universidad for inviting me to give this presentation. My name is Gonzalo Mejía. I'm professor of the Escuela de Ingeniería Industrial, Industrial Engineering School at the Pontificia Universidad Católica de Valparíso. This is my email, just in case you want to write to me. The title of this presentation is Petri Nets for Modeling and Optimization of Real-Time Production Systems. This is the agenda of the presentations. First of all, I'm going to give the principles of Petri Nets, a brief tutorial, and then I will talk about how Petri Nets can be used for optimization purposes. And then the last thing will be the David project, which is a real-life project for the industry of video games and animation, in which we use this approach for both things, modeling and optimization. Just in case you don't know, this is a Petri net. You can see there are basically two kinds of nodes. You can identify places, the circles, and transitions. You can see this graph is bipartite. You can see arcs go from either a place to a transition or from a transition to a place. The last thing that you see are the tokens. These black dots reside at the places and represent the truth of the condition or the action that is associated with each place. These tokens, as we will see, move throughout the net by the effect of transition phi, but we will talk about this later. So again, places represent actions or conditions, and transitions represent events. For example, this is a place, this is an action or a condition. In this case, it's a condition which is job in queue. This is a transition representing the event a job starts its processing, and tokens, as I said, represent the truth of the condition or the action of the place. For example, we can say we have one job in queue, or we can have two jobs in queue, or we don't have any job in the queue. This is how a Petri net works. As I said, tokens move throughout the net by effect of transition firings, but before transition fires, it has to be enabled. When you say enable, you say each of the input places of the transition must have at least one token. In this case, we have one enabled transition, which is T1, because its input places, which are P1 and P4, have a token. T2 is not enabled because it's only input place, which is P2, doesn't have any tokens at all. When a transition fires, this is what happens. It removes one token from each of its input places and puts one token down at the output places of the transition. In this case, we remove one from P1 and from P4, excuse me, and then we will put one token at P2. Now we have one transition, which is T2, which is enabled, and we can fire this transition. And in this case, because the transition has two output places, we will put one token on both of its output places. In this case, it will work like this. And at this moment, we don't have any live transitions or enabled transitions, and basically the net finish its execution. This is how it works. Why we want to use Petri nets? There are several reasons. Basically, they capture all the essence of many discrete event dynamic systems. In particular, I mean, focus my research on production systems. So typical things that occur at the shop floor are, let's say, batch sizes, multiple resources working on one job. You can model like Kanban systems, Conweb systems. All these things can be modeled with Petri nets. These Petri nets can be either deterministic or stochastic if you do put like stochastic processing times on either the transitions or at the places. But it's not only modeling, we can also do lots of behavioral and structural analysis on the Petri net. We will talk about later about the properties of the Petri net that we can check with either algebra or by simulation or state space analysis. And the nice thing about these Petri nets is they are compatible, they're amenable with optimization algorithms. We can work on both exact methods and heuristic methods, and even meta-heuristics. If you're thinking about like genetic algorithms or simulated annealing, that can also work with the Petri nets. This is a topic that is open, but still can be done. This is a simple model of two jobs that are going to be processed by one machine. In this case, you can see job A is available, job B is available, and then the processing, and then at the end, we have the jobs finish their processing. And we have a condition which is machine available, similar to the cashier available in the previous example. And now we have something that is called a conflict. In this case, a conflict means that there are two transitions that are enabled, that are active, but only one of those can be fired. And we need a mechanism for solving these transition conflicts. We will see how they are solved. This is a very simple model, but we can also model more complicated things. Something like a flexible manufacturing system. In this case, we have workers, we have machines, we have, for example, alternative routes. We can have workers with different skills. All these things can be easily modeled by Petri nets. And of course, can be much more complex. Some of the properties that we can verify with Petri nets are these. Reachability, which is the most important property from my perspective. Basically, we have two states, and then we can see if one state is reachable from another state. This is a very complicated problem. Another problem is boundedness, which means the number of tokens at the net remain finite. So there's no way we can have infinite number of tokens. Another important property is liveness, which means that at least one transition must be enabled out of times. Or another related property is quasi-liveness, which means that a transition is eventually enabled, at least once in its lifetime. And the last property that we can check with algebra is reversibility. Basically, we can verify if we can go back to the original state, the home state, which we call the initial marking. As I said, the most important property is the reachability, and this is associated with what is called the reachability graph of a Petri net. On the left, we have a Petri net with 4 places and 4 transitions. And you can see on the right, there are some numbers. For example, 100 means the current state of the net. I don't know if, yeah. So that means P1 has 1 token and the other places don't have any tokens. But if we fire transition T1, we reach this state. In this case, P1 won't have any tokens, but P2 has 1 token, and the other places don't have any tokens. And it goes on like this until we eventually reach one state in which there are no enabled transitions, which is when a token reaches place P4. These nodes, we will call them markings. Basically, a node is a marking. And as we can see, the Petri net is a compact representation of a state space. And with the optimization, we will basically search this state space for a basically lowest cost path. Basically, this is how it works, the reachability graph. You can see these are the same Petri net. The only difference that you can see here is one token corresponding to this one. Here is one token corresponding to this one. Here is one token. So the distribution of tokens is what makes these Petri nets different. The marking of the Petri net is what differs from one to the other. If you have any questions, please ask. You can interrupt at any time. And of course, I will repeat the question just to our colleagues throughout the world, I guess.
Actually, we have people in Universidad.
Probably they're familiar with it. Okay. Optimization with Petri nets, what is it? Basically, we have an initial state, and we have a desired goal state, and we want to find the cost of the path, which is the lowest cost, or the minimum path cost. For example, here, basically, we have two paths. If we will say this is the initial marking, and this is the goal marking, we can go either this way, or we can go either this way, and there are costs associated to firing a transition. And we have to look for the lowest cost path. So this is our problem. In other words, in terms of the Petri net, what we do is fire the transition in some order, has to be valid order, and find the cost, and we will have to, we look for the lowest cost path. If we're talking about scheduling, that will be the analogous of makespan, which is the completion time of the latest job, the last job. But these algorithms can be used for many things, or these models can be used for many things. But here is for makespan. And we can map the transition firings, the sequence of transition firings, into a schedule. Basically, a transition firing is either the start of an operation or the end of an operation. The time between these two transition firings is the operation time, and we can put it on a nice Gantt chart and have what everybody is looking for, which is not a Petri net, but a Gantt chart. What we can do? How can we look for or search for this lowest cost path? Basically, this is the first approach. We can generate the reachability graph and perform a through search looking for the lowest cost. But even for small systems, this thing can be huge, and this is not a feasible thing to do in practical terms. The other thing is what most people do is resolve the transition conflicts. When we have one arc coming out of one place, pointing to a different transition. Like this, we have to look for a solving mechanism. It can be dispatching rule, or it can be probabilistic, or we can have priorities. These are the common approaches. Or we can intelligently generate the portions of the reachability graph and do a search. And this is the approach that basically I've been using for the last, I would say, 10 years. In order to do this, we use informed graph search methods. I don't know if you're familiar with them, like A-star search, best first search, all these things. Just in case, this is how they work. We have an initial node, and we have a final node, and we have to find the path. The second step would be, given that we only have one start node, put it on the list of candidates, and then we start expanding these candidates according to a selection criterion that is basically established with a cost function. This cost function has two components. One is the real cost from the initial marking or initial node to the node that we're evaluating, and then an estimate from the cost from that node to the desired final node, which is the difficult part to do. Basically, we keep expanding these nodes until we eventually find the goal node. And if we guarantee that the evaluation cost function is a lower bound for the problem that we are solving, eventually we will find the lowest cost path, and that would guarantee the optimal solution. Of course, it's not practical for most systems unless you have a very, very good estimate of the lower bound, which is, for the most part, very difficult to do, especially in scheduling problems, which are the ones that I've been working on. Now, I'm going to present some of the results of my research. Basically, we have to put some limit to the state expansion. And what I do is a combination, a hybrid between two algorithms that are very common, the beam search algorithm and the A* search algorithm. The beam search only expands up to, in this case, we say beta nodes on the reachability graph at each level of the reachability graph. And the A* search is an informed graph search that expands the nodes according to the cost criteria, the total cost criteria. Just a brief explanation on how it works. Let's say we have on a Petri net the initial marking, and then this initial marking has 3 children nodes. The number of children is given by the number of different transitions that can be fired at any time. So, because we have selected to choose only 2 nodes from each level, we select the best 2. Let's say we get rid of this one, and we keep the other 2, and we expand these 2 nodes into their children nodes. Now, from these 4 children nodes, we pick the best 2. So we get rid of these 2, and then we again expand these ones, and eventually we keep doing this until we end up finding the goal node, which is this one in yellow. And the next step would be go back and retrace the path from the initial marking to the goal marking. Some details of the algorithm. We also use upper bounds to further eliminate nodes. Basically, if the lower bound of a node is greater than the current upper bound, we get rid of these nodes. How can we generate an upper bound? Basically, we do a depth-first search algorithm combining some sort of heuristic rule. In this case, we use dispatching rules like you're familiar with scheduling, SPT, ADD, whatever rule. What else? For each node, we have 2 evaluation functions. One is the lower bound, which, as I said, is difficult to calculate, and an upper bound. So in the case of ties, say 2 nodes have the same lower bound, we go and find an upper bound, which is a much more precise estimate of the cost, and that we break the conflict. And the branching is typical best nodes at first. In later versions, I also use not best node, but according to the level in which each of the node is located. And we trim, we fathom, basically we keep the best beta nodes at each level of the graph. Other nodes are permanently eliminated. The idea of the tests that we perform is not to design a very specific algorithm for each one of the oil production systems, but have something generic that can be eventually useful for a practitioner. Most of the research is focused on one particular problem with these particular constraints, and the algorithm works only on that. Basically, we have looked for many different types of problems. The first the first test that we did was on job shop scheduling problems. Just in case you don't remember, here's the definition of what a job shop scheduling problem is. An extension is a flexible job shop problem in which we have parallel machines on each workstation. More complicated problems, this is my definition. I call them flexible manufacturing systems. In this case, we have material handling, we have alternative routings, we have job batches, and buffers of limited capacity. We have many things. These problems are from the literature of Petri Nets. The other ones are the common OR library type of problems. We tested also on the RCPSP, the resource constraint project scheduling problems. You know, there are n jobs with precedence constraints and resource constraints. And the latest of my research is focusing on deadlock-free scheduling, in which we have a manufacturing system which doesn't have buffers. So basically, the next machine has to be empty before I proceed. And this can be very, very difficult problems. On the first test, this is, this research has over 10 years. They are the first test that we do on these problems. We have the optimal solutions are very common. And we have the results of my algorithm, the BAS algorithm. And we see that in most cases, we are just below 10%. These are, as I said, an old test. And still, but we have a very good computer times. These computer times were recorded 10 years ago. So probably in a computer today it would be much faster. And this is the reference where we published these results. By the way, 10 by 10 means 10 jobs, 10 machines. The second set of problems were flexible job shop problems. As I said, a flexible job shop has parallel machines on each station. And in this case, we tested a different objective function, which in this case is total tardiness. And we compare our results against another general purpose algorithm. We didn't want to test it against, very specific meta-heuristic taboo search with the IIIO, whatever. And in all these problems, we found better solutions than the shifting bottleneck. And the computer times, in this case, we had access to the shifting bottleneck algorithm, which was one of the first algorithms for job shop problems, are very comparable. So we tested this on the same computer. So it's not like I read it and I just transferred the results. And I just ran the problems. And this is again the reference. Another set of problems. That's what we.
I have one question.
Sure.
What's the largest instance that you can solve in the job shop schedule?
Well, solving to optimality, I don't know. Probably very, very small. But to find a solution in decent computer times, I would say like about 20 jobs and 10 machines, probably. Of course, you can adjust the speed of the algorithm with the beam parameter. So if you want to have a very quick solution, you can just put beta equals 1. But if you want to have a better solution, beta equals something. Well, this is another advantage. You can adjust the speed of the algorithm.
There was a current, your version of the shifting bottleneck is the original version of the shifting bottleneck, the one that tries to minimize signals.
Yeah, but that was adjusted to the total tardiness case. That the algorithm was originally thought for the make span problem, but later there were modifications to handle due date related objective functions. These are the third set of problems, the flexible manufacturing systems scheduling problems. We are comparing our results against another algorithm, which is DWS, which means dynamic window search. It's another Petri Net type algorithm. And we found better solutions, not by much, but still we found better solutions. These are the best, and these are also the fastest solutions with a minimum width, beam width. This is with another. And this is what the problems are about. Basically 50 jobs, 3 machines, alternative routings, varying batch sizes, recirculations, something that is not very common to handle by traditional algorithms. Our 4 set of problems are the excuse me, the RCPSP problems, project resource constraint project scheduling problems. These are the typical problems that are published on a PS-lib library. They're very, very common. There is a huge set of problems. It's impossible. Well, it's possible. It's not practical to enumerate all the problems, and basically we put the average gap and the number of solutions. So we have a set here of 100 problems. There are almost 500 problems, just the 30 activities problems. In all these cases, our gap was 0. We found the optimal solutions in all of them. And you can see also the computer times were very, very short. This is recent work. This work has about 2 years. And we also have very good results for the 60 and 90. And on the 120 activities, we have, I would say, very decent results for an algorithm like this. These are the renewable resources. In the non-renewable resources, Petri Nets are probably more attractive because we go into the issue of deadlocks. Because they say, in non-renewable resources, eventually we run out of some resource, typically money or some materials eventually run out. So there's no feasible schedule. In this case, in all these problems, we also find the optimal solutions in most of them, and the maximum gap was only over 2%.
I have another question.
Mm-hmm.
Do you improve the current bounds for the 120 jobs in the PS period?
No, not at all. No. And I anticipate that I won't be doing this because this is not an algorithm for that kind of problems. We don't check like the dominance rules and all these things. This is very, very general. In fact, we use a very, very simple lower bound, basically the critical path. Very, very simple. And it was on purpose, because we knew we weren't going to beat the best algorithms out there. It's not on purpose. But the purpose was to put these algorithms on a real setting and see how it works. The latest problems, which is a work that is still in progress. Hopefully, this year will be published. We compare. This is another kind of problem that we call it like deadlock-free scheduling problems, which we have no buffers, and a very, very tight coordination is required to find just a feasible solution. It's not solving transition conflicts, just probabilistically you will end up in a situation which is not a deadlock situation. And we are comparing against the latest jobs that are published. This is last year. And these are published on top journals in the II transactions. And in all these problems, we found better solutions. So essentially, I would say these are the best known solutions for these problems. In this case, it takes less than 1 second, of course, depending on the beam width. So we run the problem many times and report the best solution. But it's not probabilistic, so we run it again and we will find the same solutions. Now, let's talk about a real system. This is the last project that I worked while I was a professor at the Universidad de los Andes in Colombia. If somebody from there is listening to the presentation, hello. This is the Proyecto David, which means development in animation and video games. And basically, the idea was to create world-class industries in the animation and video games sector in Colombia. This project has several, I would say, branches. Education, how to use video games for teaching and education purposes. Free software, how to help companies to use free software, which is not an easy thing. Optimization was my part, and also the best practices in project management for this particular industry, which is not the same as construction project management. It's very different. And the latest project was paper and pencil, which is drawing to help a child, a kid, to just draw scribble something, and then out of there you get an animated product. And my part was consisted of modeling, scheduling, and execution. The project goal, as I said, create world-class companies in Colombia. There were some companies that were involved in this project. This was a Colciencias project, which is the equivalent of CONICET here in Chile. Companies dedicated to animation, video games, and also music. What we call digital content. Just to give a brief introduction, all these digital content projects have 3 steps. The first is pre-production, which is like the creative part. Then we have production, which is basically like an assembly line, has to work around the clock and everything is set. And actually, they use the Kanban methodology to control the projects. And finally, post-production to polish the product and sell it to either to a publisher or to the final customer, just in case. This was one of the video games, Antarctica, that was created as part of this project. Well, we saw some relatively simple example of Petri Nets with 1 machine, 2 jobs, or 2 machines, 3 jobs. But if we have something more complex, Petri Nets are complicated to use. Say we have 200 activities and, I don't know, 50 resources, that becomes very, very cumbersome to model. So we given that now we have a mapping one-to-one between this standard, which is the BPMN, Business Process Model and Notation, which is widely known by most people, not only in the universities, the research community, but also in industries. We can, under certain rules, convert BPMN diagram into a Petri net, and we use the tools for analysis and for optimization that we saw throughout this presentation. So basically, we model the activities of a project with this BPMN standard. There are many editors out there, like Visagi, there are some others, that is easy to do, is easy to understand by these project designers of animation and video games. And now the thing becomes transparent, and we do the analysis, and we output the schedule of a project like this. So basically, this is what we do. We have the BPMN process editor, and we can do the mapping. We do the mapping one by one. So basically, this translates into this. And there is another advantage that we can use hierarchical modeling. Petri Nets are also compatible with hierarchies. So say at the top level for general managers, we have 3 activities: prep, production, and post-production. But once you go down the structure, you can go to the very details of rendering and rigging, all these activities typical of this industry. And calculate the schedule, and then we export this schedule. We can export it via XML to Microsoft Project, or well, it depends on other commercial software project management packages. We are not intending to replace Microsoft Project, but to enhance Microsoft Project. This is an example. This is a simple example of a video game. It has about 20 activities. We have the times, we have the resources, processors, and everything. And we calculate the schedule. We also calculate the cost, resource utilization, and everything. And we can also do some discrete event simulation. We can put like a stochastic processing times and then run the simulation, just like a arena or pro model. Of course, this is not a very, very complex video game. Probably it will take more. It will take longer just to model this and then map it and then. But there are complex projects like this. This is a project which is called El Chavo Kart, which has 220 activities and about 5 workers with different skills, and generating the schedule in Microsoft Project is kind of painful, and if you want to reconstruct the schedule, add activities, it can be a little difficult, but we can do this easily with the BPMN, and then find the schedule. Another thing is we have, the algorithm works fine, works very, very well. But for the project manager, like optimality is a concept that doesn't exist. But for them, one thing that is very important is to have a feasible schedule in terms of resource assignment. Microsoft Project, you can over-assign a resource. And so basically you say, this is the schedule, but this is not a feasible schedule. And for them, the quality of the schedule is measured on how much over-assignment there is. Last, there are many things that can be done with this approach, like investigate other Petri Net-based algorithms. I have some work on meta-heuristics, specifically with genetic algorithms. There is also work on particle swarm optimization, and probably can be mixed with IIIO or some other things. Multi-objective optimization is something that would be nice to work on. Multi-project optimization. This is very particular, the video games. One of the issues in this industry in Colombia is that, for example, Pixar comes to Colombia and say, hey, I want to have, I don't know, 200 hours of running time. Who can do that? In Colombia, nobody can do that. In Colombia, nobody can do it. So say, I want 200 hours of running time in, say, 1 month. Nobody in Colombia can do it. So the only way to accomplish that is if you have multiple companies working at the same time, probably sharing resources and probably sharing also projects. That's why the issue of multi-project optimization is interesting. And also look for another applications. Now that we are here in Viña and Valparíso, port logistics is a very complex problem in terms of coordination. Petri Nets are very good for that. Perhaps mining, and perhaps you have your own ideas. This is it. Thank you for attending this presentation. My coordinates are these. This is my email. Please write to me. If you want, you can contact me for anything. If I'm interested on these topics, just let me know. Thank you.